Hey there, Brian.
Hey, how's it going?
Still some echo here. So, okay. All right. Getting rid of the echo. Going all right. How are you?
Doing good. Cold here in Seattle.
Yeah. Starting to get a little cold everywhere. I was just reading the news this morning before this conference started about how there's going to be a severe winter storm that's once in a generation. But I feel like nowadays
happen every year.
everything's once in a generation. Yeah. But anyway, that's a topic for a different day. Today, we're going to be talking about multi-level IR and ZK with Brian from Risk Zero. And so, Brian, I'll let you take it over.
Great. Hello, everyone, and thanks to the Manta people and the OpenZL people for inviting me. I love these kinds of discussions, and it's really interesting to see these kinds of sort of use cases pop up in multiple industries over and over again. So let's see. Okay, so if you look at the state of ZK, and if you were around for the last really sort of hot hardware-software interplay problem, sorry, this chat window is very distracting. Got to figure out how to minimize it here. Yeah, so anyway, ZK resembles the sort of early days of AI, and you see a lot of same kind of problems popping up. You have these very tightly vertically integrated development environments. People are building custom languages. It's very difficult to extend the sort of runtimes to support new hardware. There's not a lot of access to various debugging tools. Sort of trying to, if you're thinking about building custom hardware, trying to create a tight loop between feedback between like how well your hardware is performing on a variety of problems. This process called software hardware co-design, which I'll talk a little bit more about in a bit. Very difficult. And then you have like a proliferation of sort of core technological approaches. And I guess an analogy from the early and or current AI days would be, whether capsules were going to win, sort of which nonlinearities were going to really end up being dominant, things like this. So you can see that a lot of parallels to all of these in ZK with sort of the number of proof systems, the rapid pace of mathematical advances, the sort of clear, I wouldn't say need for hardware acceleration, but potentially opportunities to expand the capabilities of these systems through the creation of custom hardware. And I think that extends past ZK all the way into FHE and other kinds of advanced cryptography. Okay, so talking about compilers in ZK, I realized that it can be kind of confusing because you have code and it's really unclear exactly what your compiler is going to compile based on exactly what kind of system you're using. So it might just be creating IR for another system. You could be outputting an arithmetic circuit. You could, depending on which team you are, actually be outputting Verilog for real hardware, or you could be using a compiler to say produce like CUDA code to run a GPU optimized version of your prover, which is something we do. So there are a lot of uses for compilers in ZK, and that's a bit different than AI because you don't necessarily see the same kind of like physical versus arithmetic circuit split. I want to go over some examples of compiler stacks because I realize not everybody is super familiar with compilers, how they're used, and what how code tends to flow through. So there's generally this concept that you're starting from some higher level of abstraction, and then your compiler is sort of lowering these things to lower and lower level of abstractions until you get down to something that can actually run on hardware. So, Rust itself has two layers of sort of transformation that happen before it gets down to LLVM, which then, of course, depending on which hardware target you're actually targeting has its own massive other sort of abstractions and optimizations that it goes through. And you can see these patterns in AI as well, except for it's even, I would say, more complicated because you have code like PyTorch code or JAX that is technically written in Python, but generates effectively an IR that is well, depending on which approach you're talking about, like generates a computational graph with a bunch of these kind of kernel nodes in it. And then maybe you lower that down to a different language where you start thinking about laying that out on hardware, so forth and so on. Okay, so compilers in general are doing this process of progressive lowering, which is what I was sort of talking about. You take code, and then you start to think about it at whatever level of abstraction it's at, and then you emit code that is less abstract or closer to the sort of goal code you're trying to generate for your hardware, and you keep doing that process until you've sort of gotten code that's as optimal as you can get it at the time. So hardware and software co-design is this interesting process of trying to, if you're going to build new hardware, you probably want to know how it's going to perform on the most interesting use cases. So if you think about the process of actually developing that, you have to think, okay, well, what are the most interesting applications? So some of the other speakers here have talked about, looking at NTT and MSM as kind of the sort of key technical problems to solve. But that might change over time, and as you dive into other proof systems, you might identify more and more target use cases. So then you have to figure out how to write test cases for those target use cases, so you can assess how well your hardware is performing against them. But then, of course, you have a variety of choices of languages to write them in, and depending on the proof system, you might not even have a language, and you might just be using something that looks more like assembly. And this is actually something we're running into in a benchmarking project that will be fun to talk about once that's done. Then once you have identified all these target use cases, you then have to compile them for your hardware that's not done yet. Then you have to figure out how well this set of use cases for an evolving industry is going to perform on hardware that isn't done yet, and then keep trying to use that kind of data to inform alterations to your compiler, the hardware itself, and it's a sort of giant loop. So it's the sort of ultimate test case for, or not test case, but the most demanding case for building software and hardware systems in a particular vertical. So I just talked about some of this, like why this is hard. You have to pick languages, frameworks to use. You have to plumb support for your hypothetical hardware through those systems. Maybe in ZK's case, you can implement support in ArcWorks for your particular chip, and maybe that gets you access to a number of proof systems, but not all of them. And then you have to design and emit an IR that spans your use cases. OpenZL is a good example of an IR that spans a couple use cases and proof systems. Then you might have to optimize the IR for multiple hardware designs and repeat. So I love this XKCD comic, and I think this is very true in the deep learning space. And it's not necessarily meant to be a cautionary tale, but just there's an explosion of a million opinionated approaches, often driven by very large software entities trying to build a bunch of different middleware, including a project that I was involved in, listed on the right, PlatML. But you've seen the industry kind of coalesce towards a smaller set of frameworks. People might take issue with which frameworks I put in which category, but the point here is that there's going to be a sort of process that I imagine the industry will go through in building up various IRs and sort of testing them against reality and kind of iterating. I do think, though, that there is an interesting, a particularly interesting sort of survivor from the last round, and that's what we're going to talk about here. So MLIR stands for multi-level IR, and it's really a framework for building compilers more than anything else, and it's a framework for building IRs that solves a lot of the sort of lack of tooling problems that I was talking about earlier, and has learned from sort of the vast history of compiler development, and is very informed by the sort of last round with AI. So I would say it's used by most major hardware vendors for their AI ASICs. It's actually used inside various other like gaming consoles for networking chips and a bunch of other things. It's part of LLVM, has a fairly active community, and there's a whole bunch of really cool tools that it comes with that I'm not going to go into. So there's an example of sort of what this looks like from PyTorch. So PyTorch has its own sort of very opinionated high-level language called torch to script, but that's amenable to converting into a couple other representations, and there's a whole bunch of them that it does get converted into. But once you sort of get into MLIR land, you have these sort of standardizations around these dialects, which represent the different levels of abstractions, and then you can use the sort of LLVM machinery to transform those dialects into lower level representations that then people can have. Hardware vendors can plug into sort of the lower levels of the abstractive stack and not have to worry about which programming framework their potential customers are coming in from. Okay, so how could one leverage MLIR for ZK? So there's a number of sort of ZK-oriented dialects one could create, and in fact, if you look back at PyTorch, MHLO there, that's actually a dialect that sort of came out of the XLA compilation framework, which wasn't based on MLIR, but it was fairly easy to translate the IR into MLIR. So I would say just because people haven't built their IRs around MLIR doesn't mean you can't sort of migrate to it in the future. And we went through a lot of that at PyML ourselves. So there's a whole bunch of things one might be able to do. You can create, these sort of IRs that are targeted towards building arithmetic circuits. You can emit code for different hardware targets. You could potentially, provide, once you have these dialects, you can hook them into things like ArcWorks, which would then, in theory, make it easier for developers to, say, leverage custom hardware. Yeah, and then also, I think there's some interesting routes there for ZKML. People have done some interesting things there with TVM, and I think the opportunities for combining all of this stuff in one kind of giant compiler start to become a bit more obvious over time. So we, at ResZero, use MLIR internally to build our circuit. We're working on a couple dialects and some passes that we will eventually release, as well as probably a DSL on top of that. But that part's kind of not really the point of the talk, I guess. The point of the talk is that if you build dialects at these levels, then it lets the sort of whole ecosystem contribute by potentially building their own DSLs that target lower level dialects, as well as build different dialects, translate between them, and overall, let's say, reduces the duplication of work in sort of building a bunch of proving systems and potentially connections to hardware, etc. Yeah, so we use Zirgen internally to support several different hardware targets, as well as optimize the circuits that we do describe with it, and it supports a limited number of proving systems currently. Specifically, we use it to describe the RISC-V circuit itself. as well as build a number of accelerators for data hash functions, finite fields, etc. And we'll probably be building a lot more of those, and ideally enable the community to start using this infrastructure to build more things in the future. So a bit more concretely, what this looks like is we have a couple front ends that actually create the sort of MLIR dialects. We have a couple passes that work on the Zirgen dialect to sort of optimize it for various sort of problems, and then we take that and then emit code for a variety of backends, including like a C++, prover and/or verifier, Rust, CUDA, etc. That's actually all I had. It's just sort of a brief tour of MLIR and what one might be able to accomplish in the ZK space, and hope to have a lot more to talk about in the future. But I think for people looking at building things like OpenZL, it's a good ecosystem to start thinking about migrating towards as the industry matures.
Awesome. Thank you very much, Brian. Thank you for that presentation. And we have just about a minute or so for questions. So if anyone has any, feel free to ask in the Q&A session. All right. No worries. If no questions, then thank you very much, Brian. And next up, we have Wei Dai, who is also a cryptography researcher, and we'll be jumping over to the session now. Thank you very much.